and welcome to my talk about Let the Bytes Speak. This is going to be a technical presentation about how to write a dissector code, what to expect, what to do, what not to do, and in general, a little bit of cookbook on how to proceed when you write a dissector. My name is Roland Knall. I'm one of the Wireshark co-developers. I've been a software developer for the better part of 25 years now. My day-to-day business is as a team lead and team manager for an intercom software development team. You can reach me on Twitter most of the time. You see my Twitter handle there if you have any questions, and I'll also be later on the Discord channel as well, mostly in the developer then. So let's dive right into it. What to do when you want to write in dissector. So we're going to go over the do's and don'ts, a little bit about what are the ramifications of writing dissector code, about the background of writing dissector code, what you should avoid doing, and what you absolutely must do when you write a dissector. We're going to dive into the features and techniques. We're going to use an example dissector or example software part that's already been distributed with Wireshark, which is our example XCAP code, and we were going to write a dissector for that. And in the end, we're also going to talk about a little bit of preparation for the code and what to do and how to submit code to the Wireshark repositories. So let's dive right into it. What to do when you write a dissector? Well, if you're going to come fresh to the project and if you're going to come fresh to the dissector, the first three things you should recognize are the who, what, and how of writing dissectors. Who is more of a general direction. So who is doing the dissection should be your main focus when writing the code. What is the level of knowledge? Is your target audience experienced technicians who already know the protocol, who already know the hardware, who do the section of that protocol on a day-to-day basis? Or are you writing a dissector code for your end customers who use the protocol rather rarely or superficial and just need to dissect or find a certain problem? This goes into how the naming of your values are, how deep you want to integrate the protocol and stuff like that. The level of expertise is actually quite important because there is a lot of things you can do with the dissector. You can make it automatically tell people what a certain value means. You can have speaking names, or you can just have abbreviations that are referenced in some RFC manuals. And thirdly, the level of networking experience in general. I think if you work in a network engineering field, you most certainly have your basic level of knowledge down, but most people out there have a very limited or no knowledge of the basic inner workings of network environments. And this especially comes true if you go into environments who have no direct interconnection with the network per se, like for instance, industrial automation. Industrial automation uses a lot of Ethernet stuff, but most people there have no clue about how TCP/IP works, how UDP works. So if you write a dissector for those kind of levels of fields, and if this is your main target audience, you also have to take into account how to phrase certain stuff and how you provide the documentation for your protocol. The next thing is actually, it looks trivial, but it's actually one of the bigger topics. So what will be dissected? For instance, if you come to a payload protocol where you have about 20-25 bytes of payload and you just want to put out the information in this protocol, then you just can list the individual fields, the individual elements, you're done with it. But your people might, or the people using the dissector might not necessarily be the ones who are interested in the same parts of protocol. For instance, again, in industrial automation, the most dissected or the most used scenario for Wireshark is actually to figure out if deterministic behavior has been achieved. So if packets behave the same, come in a timely fashion, and if the delta times between packets is often the right amount. So the people are not really interested in the payloads. They usually skip that part over, or there are even tools that don't capture those parts of the packet. They just capture the first about 60 bytes of the packet, but this is all they need and this is all they require. So your protocol should expect not to see the full fields, the full information that has been transported on the network, but still be able to provide valuable information like request, resend, response correlations and stuff like that. Also, when you tend to implement a dissector and you come off a certain specification, you usually do that in full. You really set up every value that there is. There might be some values that are very esoteric, which are never ever used. It still makes, from a completionist point of view, sense to put that into a dissector, but to put it prominently would be overkill in that regard. So you might hide that, especially if it's like a field that's just one hardware in 1 in a million parts will do that. Also, and this is some additional thing, think of parts that will require additional analysis. So for instance, if you transport a payload and if you have in this payload a certain other protocol, think ahead, which parts of your dissector will contain other code that will be dissected by this software versions, or also which parts will collect raw byte data that you might need to export later, and certain scenarios like that. Also, something that has to be considered is how will it be dissected? Now, you're usually pretty familiar with a generic dissection setup, like you have your PC, you attach it to a network, you trace on a specific monitoring port, or you have a tap device, or you have some in the middle device which allows you to see the packets. But this is usually a live analysis. Now, there are protocols out there who won't be dissected in a live sense, but in an offline use case. And in that regard, you can take as much time as you need to really properly train your dissector and to calculate additional values, to calculate additional fields, to reassemble data, desegment, defragment data, stuff like that. But if your protocol is running on a very fast load network, and if the main interest is going back to industrial automation and going back to big company backbones, is just to see what's happening right now and not to go into the details, then you might rewrite your dissector in such a way that it is really fast in getting the top view of the protocol. And if that's all there is, and if that's all the packets there are, then it ends like there. And then you can go into a deeper dissection if it's an offline version. Also think of time constraints. Now, I'm going to go into how Wireshark and the dissection engine in general works later, but think of it like that. The faster you are done with your dissection code, the better it is for everybody else. So if you take a lot of time in your own dissection code, you're going to have a bad time dissecting a large number of packets. And this usually leads to scenarios where users tend to look to other tools or don't use the dissector in the most common way because they say, okay, it takes me too long or I can't achieve my use cases. So really think about that before you start writing the dissectors. Lastly, most dissection is nowadays, most live dissection is done using T-Shark. So if you're using T-Shark, you should really have a possibility to get the fields you need with a certain name and to be able to have a live capture in, let's say, a console window, which just scrolls by, but it's still providing useful information. So if you're relying on having a deep dissection, a deep hierarchy, a lot of hierarchy elements, this is not very useful for a T-Shark dissection. Again, think of what is the use case, what is the general use case here, and write it for that. Point that is often overlooked is the legal ramifications of writing dissector code. Now, if you are an open source developer and you develop your own protocol, then you can write the dissector code because it's basically your stuff you're documenting anyway, and it's kind of a documentation you're using to get your stuff across, to get your protocol across. But if you're working for a company and you write the dissection code for the specific company, you most probably are not the copyright owner of the protocol. Now, you might say, okay, it's just a few bytes, it doesn't really say anything, but from a legal point of view, you really are in hot waters if you're not having some kind of allowance by a boss or some kind of clearance for distributing this code. The code itself is not even that biggest a problem. The biggest problem is who owns the specification. Now, for IEEE, everybody who had an IEEE abonnement at one point knows they charge quite a lot of money for it, and they don't really like it if you then write a dissector of it without any kind of contribution. So if you're working for a company who pays for that, that's fine. But again, ask if you're allowed to distribute that code. And the third thing is trace availability. So when you write a new dissector, we in general ask you to provide some sample captures. Now, those will contain some information that, especially in the EU, is covered by the GDP, or as it is called in German, the Datenschutzgrundverordnung, which basically means that you have to strip it of any sensitive information that is contained in such packets. That might seem trivial, but it can be used in certain areas, for instance, of IDing certain computer systems, and that, again, is really problematic. So you have two options here, which you have a multiple of options, but I just named two. One is SCAPI. I see I wrote an E instead of a Y, but the URL is the right one. SCAPI is a Python toolset which allows you to generate packets on the fly, and you basically write up whatever packet you want to do. So in this case, you're already producing generic information. You're not producing it off live systems, and then you're okay with that. The second thing is Trace Wrangler, which allows you to anonymize packets to a certain idea, or rearrange or remove information from packets that otherwise might lead to an issue. So I would strongly advise, if you provide us with traces, first of all, provide us with traces which cover every part of your dissection code, so that those traces can then further be used in fast tests and other testing scenarios to ensure that your protocol stays valid and stays correct over time, even if we change something in the backend. And the second thing is, make sure that the information provided in those trace files doesn't contain any sensitive information. It might not be seem sensitive to you, but it might be seen sensitive in the sense of the law, and therefore take extra care with that step. Now, if you've done all that, and if you have a good idea in mind what you want to do and how to write your dissection code, the first thing you're going to do, obviously, is read the documentation. I mean, we're all reading documentation on a day-to-day basis, right? It's a fun thing to do. It's very uneventful. So there are two big documentations, and the first one actually seems kind of arbitrary to mention at all, but it's the user guide. A lot of dissection code gets written with just a certain use case in mind. So you have this protocol, you have this idea, and you want to see the fields, and that's what you want to do. But when you thought about who else wants to see those fields, then you might also think about what they might do with it. If you run to classes like for Jasper and Betty, you're gonna see that they're using Wireshark in a way different sense than you might be using it already. If you start coming up with display filters and capture events, and you can have redissection stuff and so on, preferences, just read the user guide and see what's possible with Wireshark and see how that could be beneficial to your dissection. The second thing you should absolutely read is the development guide. Now, I don't recommend to read it through at the first step, but at least glance over the overview chapters and get a sense of how development in Wireshark works. And especially go over the chapter setting up the development environment. The last source of information, and this is just an entry point because there are a lot of README files. I'm going to show you the directory later on, but the main README file for writing dissector code is README developer. The reason for that is that we state a lot of obvious things that might not be reflected in the developer guide itself, which you can use or which you can set for dissection. For instance, what we state in there is that you have to run certain tools to sanitize your code, to avoid certain functionalities on systems and stuff like that. Also, keep in mind that every code you are writing, you're not writing for your system platform of choice. So if you're a Windows developer and you're writing code, and you might be used to using certain C++ stuff from Microsoft Visual C, then you're gonna run into issues because with GCC and CLang, which are the main compiler suites used on Linux and Mac, those commands might not be compilable. So you always have to keep in mind that your system will run not in your development environment of choice, but has to run also on Linux and Mac. We focus very, very strongly on having this cross-platform compatibility, and we, in 99.9% of the cases, do not allow code into Wireshark, which runs only on a single platform. I'm going to show you this in a second. So we have a tools directory. In there, you're going to find a lot of setup tools, and those setup tools allow you to create your development environment. Now, jumping, sorry, this is the wrong, jumping back into Visual Studio. So you see here, this is the general Wireshark repository. The two things I mentioned already are the README developers. So when you go into doc, you're going to see a lot of files, but there is your README developer, which is a general how-to for Wireshark developers. And it should always be a starting point and at least read the first few parts. You don't have to go through the main README files and go to everyone, but at least README Dissector is a good overview on how the dissection engine actually works. And you might go through that and see that a lot of ideas you had of how you want to dissect your protocol actually differ from how we do stuff. And so you can benefit from that. The second directory I already mentioned is the tools directory. Now in the tools directory, we have quite a few files which should help you checking for certain not allowed API functionalities and stuff like that. But it also contains, like for instance, here you have the check functionalities. Check APIs is the one I mentioned about the API files. But we also have a lot of stuff that's called blah, blah, blah minus setup.shell. So if you go in there and you execute that, it will set up a development environment on your system of choice, which includes all the necessary libraries and development libraries to compile a basic set of the Wireshark platform. It might not contain all of that. For instance, it won't contain some of the speech codecs used in zip and RTP. But it will contain about 95% of what you need. If you're required to do also those libraries, you will have to do it yourself, which is not a big hassle, but it's just we are not allowed to redistribute some kind of development toolkit for that. There is also, we have some for Mac, we have some, this one uses ports, this one uses Homebrew. We have some for Ubuntu, there's Red Hat in there, RPM setup can be used for that. And yeah, here we have our Windows setup as well, which is a PowerShell script. I'm not sure which tool we're using at the moment for that, but it's also, it will download all the necessary tools. We have our own repository where we keep those packages up to date. You don't have to compile it yourself, but you can use this tool to update automatically, and then you can choose if you're building for Windows 32 or 64. And it will create a development environment for you where at least be able to compile. So this is how you go through and create your development environment. The last step in creating your development environment obviously is choosing your development engine. So as you have seen, I'm using Visual Studio Code. This is a personal preference. You're not forced to that. So you can use Visual Studio Code. Some people using Qt Creator. A lot of guys on Windows use Microsoft Visual Studio. I know a few people who use Eclipse, so it's basically up to you what you want to use and what you want to use in your choice of system. Coming to the fun part. Now, naming conventions. Naming conventions are never fun, but sorry, I have to go back. I would venture a guess that a lot of you guys don't know that we have something called display filter reference. So if you go on to the ref, let's start with the main display filter reference here. You will see every protocol we currently support in our source code and every field of that protocol, and even you get information of since when this protocol has been supported in our source code up to which version. So there are some protocols in there which have lastly changed at this version. They're still, I think, in there, but they are not supported anymore. So let's jump to a popular one. Go to TCP. So you see, okay, we started TCP support with 100, obviously, and it's been supported throughout 346. So you won't see development versions here, but these are just released versions. Inside this display filter reference, you get every information. So you get the field, you get the documentation, which is part of the dissector code, and you get the type, and also from which version to which version this field has been supported. But you already see, and this is the good thing about it, you already see how you can structure your protocol. So in this case, okay, we have TCP, which is the main name of the protocol. And then he says, okay, he has some parts that he wants to analyze. So this is something that the dissector has generated. This is not part of the original packet, but it's something that the dissector has deduced out of the information presented to him throughout the packet and also throughout the stream. So he doesn't only look at a single packet, but he looks at the way multiple packets are connected to each other, and he deduces some information from that. And by the deduction, he then generates fields which are not necessarily part of that. And he can then generate fields out of that. And you can use that to dissect then your sub-dissection engine, stuff like that. So you see a few practices here, which are actually good practices. So you have, for instance, the TCP flags, which are a single field. So you can actually go into this flag, but you also see in each individual field for the flags. Now, everybody of you obviously knows those. Just a disclaimer, I know those I need to know, so don't feel bad if you're not knowing every one of them. But you see, okay, I know when I'm writing a display filter that if I go and I need a certain flag of the TCP dissector, I know TCP and I need a flag, so dot flag, and already the Wireshark will tell me, okay, there's a subfield that's called flag, so I'm assuming that one. Hit dot, and then I code to acknowledge CVR, ACN, FIN. So it also already makes sense because those are the field names I will find in any RFC document. So if I look up the RFC and I know, okay, I want to have a dissection for that certain flag, then I can immediately from the RFC document reference how the display filter will be named and vice versa. This is a good example of how to do that. Now, the TCP dissector has been worked on over time. It's been there from the beginning. So obviously not everything is 100% glory, but most of it is really good and most of it can be really used as an example. Now, the other side of the material of the metal, if you want to see it, is in my case, which is a really bad protocol, is OPC-UA. Now it starts off nice, but then the problem with this protocol is it has been generated. So it's not written by hand, it has been generated by a tool, which is fine in itself. But then there were some shortcuts to be done. So one thing that already is a problem is this for me is this part here. So I have an OPC-UA array dot length, which in my head is, okay, there is an array and there is a length for it. Then there is also a field OPC-UA array size with big letters instead of small ones and not a dot after the array. There's an OPC-UA array dimensions. No one will be able to use that except if you know specifically what to look for. So he will not write display filters for that stuff because you won't be able to actually look it up in a way that makes sense to you. So all you can do is you look at the protocols and that's it, which is very limited to what you can actually achieve. You can't use that in scripts, you can't filter it. But it gets worse because there are also fields in there, Boolean and Boolean S, which actually are used throughout and at many occasions. So every Boolean you have might be part of OPC-UA Boolean. If you're looking up for a specific field and the value for that, you won't be able to. Because if you type display filter OPC-UA Boolean, you will match on 1,000 things, but not, I guarantee you, not on the one thing you're looking for. So this is very, very bad. You should avoid having stuff like byte string, Boolean, generic information in your dissector display fields. And also one of the worst that you can ever have, I'm guessing they don't have it anymore, would be OPC-UA.data, just generic data. Yeah, we know, because we're looking at data. We know this is data, but you don't have to mention it. It's just name it what it is. Now, again, this is a generated protocol. So for that information, this dissector has been generated via a tool, which makes it even worse, actually, because they could have written that tool to create a dissector that works Instead, what they wanted to do is they just wanted to give every field inside the protocol a name and didn't think further. That's what actually is my problem with that. Now, it's a cool thing to have it. That's not a question. But it's, if you write your own dissection engine, please avoid using stuff like that. So actually, going back to my presentation. Yeah, now we have the fun fact that I'm on Linux and the PowerPoint presentation works like that. Well, we keep it. So look it up. You have negative examples, you have positive examples, and just do it as you would in your own way. It will work out in the end. But just keep in mind, OPCOA, look through it. This is just not how you would write the field names. Now, understanding packet flow. This is something important. When you're starting to dissecting, your assumption would be that I will get all the information I have on the network, right? Because that's what we always say, packets don't lie. Actually, that's wrong. What you get is every packet information, every byte that we have found to be handed over to us throughout the capturing engine. That's the so-called TVB that reflects in most cases all the bytes coming in through the network interface with an exemption. But in general, it doesn't have to. So you are required to ensure that if you, for instance, say, I want to read 4 bytes because those contain now a CRC of some kind or something, you have to test if you really have an additional 4 bytes to read from, because you might not have it, because your protocol might have been cut off. Remember when I mentioned earlier that in industrial automation, often you just read the first 64 bytes. The reason is those are networks which send hundreds of packets within 10 to 15 microseconds. And all they need is the first 64 bytes, the Ethernet header, because this will contain who sent it, from where, and in which time expectation. This is all they need for, I would say, 95% of all the scenarios they have for debugging on a network level. Now, all the rest of the packets will be missing. So if you run a dissector, you just have the 64 bytes. And these 64 bytes will come in the TVB. The TVB is the main data buffer we have, which contains all the dissection information. So Wireshark actually, when you come to the network, Wireshark employs utilities that capture for you. On Windows, you have the npcap and winpcap utilities. On Linux and Mac, it's libpcap, which do the actually capturing. Then you have the dumpcap capture engine, which is coming from Wireshark, and it runs as a separate utility. The reason for that is often on systems, if you want to capture from a network interface, you have to have super user access. You have the root level access. And we don't want, it's a very bad idea to have Wireshark have this kind of privileges. So what you do is you have a separate program. This program has those privileges, and Wireshark just reads from a byte executed by this program. This is what dumpcap does. It can write to the hard disk, or it can provide the live capture through Wireshark. And Wireshark in itself just looks at the DLT, figures out which is the main dissector from there. In most cases on Ethernet, that's packet frame. And it starts the dissection with that. It just gives packet frame everything it captured in a single TVB and says, well, here, go nuts. This is what I found. And everything else then happens with certain dissection protocols. Packet frame doesn't decide if it calls the IP or TCP. It really doesn't care. All it does is saying, okay, I have now these bytes, who wants it? Two things important here for you is, the first thing is you're always gonna run through dumpcap, except if you're loading files, then you're gonna run through wiretap, but from a dissection point of view, it doesn't make a difference. And the second thing here is, actually, you're not seeing everything that's coming through the interface, because your hardware might throw stuff out. For instance, the frame check sequence number on Ethernet is a famous example you won't see on Windows. You will always see with external capture devices, because this usually gets thrown away at the Mac, at the network interface. So when you want to write a dissector, you actually only have 3 things to do, which is very, very simple. You have to add the source, you have to do something with some files called cmakelist.txt or cmakelist custom.txt, and then you have to compile and you're done, right? That's very, very simple. Now let's look back at our source code. So when you download the Wireshark source code, it's going to be overwhelming at first because there are a lot of different directories you're going to use or going to need at first glance, or you're going to see at first glance that might look kind of, yeah, overwhelming. But you actually just need 3 of them. The UI directory obviously contains everything belonging to the UI. So this is where all the Windows stuff resides, and all that. T-Shirt, for instance, is part of that, because T-Shirt for us is just another UI. The second thing you have is WSUtil, which is a utility library. For instance, we have a lot of CRC mechanisms already as part of our source code. You don't have to bring your own CRC 8, 16, or whatever routine. We have most of those already in there, and you can reuse it. So if you see, okay, ADA32, we have base 32 algorithms, we have CRC 5, 6, 10, 32, 16 plane, some curve stuff. Yeah, pretty much all the base stuff that a lot of protocols are going to be sharing is part of WSUtil, and you should really use it because it's, first of all, it's optimized for speed, and second of all, it uses our internal functionality. So if you have a memory leak in your own implementation, most certainly we won't have one in ours. So you can use our stuff to be safe in that regard. The directory you're going to have the most fun in is EPAN. Now, EPAN is our dissection engine. Everything that is being dissected is residing under EPAN. And so if you're writing a dissector, the first thing you're going to do is you find a place for it underneath from EPAN and dissectors. This is the directory where all the dissectors reside. You find a lot of files in there that start, first of all, we find files in there that start with file. Some of you probably haven't known it, but Wireshark can also dissect files. For instance, you can open up a JPEG and see each information of the JPEG buffer. You can open up an MP4, but also the rest is packets. So one of those is gonna be packet. I really don't like searching via the no, packet frame actually resides one step ahead. That's why I'm not finding it. But this is basically where all your code resides. Now, let's take a look at what we want to do in this example course. So I'm gonna fire up Wireshark real quick here, and hoping he doesn't have to recompile because I just compiled it. I'm using a program here that's called XCAP example. So XCAP example, let's see if you. So XCAP example is an XCAP interface example program which just wants us to demonstrate what varieties can be done using that interface. XCAP, if you don't know, is an external capture interface. You can write your own program for it, and then you can utilize whatever capture engine, whatever capture stuff you have to capture from that. For instance, some people use it to write Bluetooth sniffers. You have some USB sniffers employing that. There are people who do CAN bus capturing, Modbus capturing, Profinet capturing using that interface. An XCAP example Py is just a simple Python routine which demonstrated and is a test case for us against that interface. So I'm opened it up, and as you can see, in general, it just presents me with data. We can look at that data information in the packet view. I'm just zooming in here, and you see we have an Ethernet frame. We have with the source and the type. As you see, this is just empty information because it's generated in the Python utility. We don't need anything. We have an IP44, an IPv4, and then we just have data. So for this protocol, we're gonna now write a dissector. The first thing we're gonna do, besides stopping the capture and stopping Wireshark, is we find a place for it. Now, the protocol itself is called example. So our dissector is gonna be called example, because why not? And the first thing I'm gonna do is I create a new file underneath dissectors and call it packet example.c. Now, in general, you can only write a dissector either in C or in Lua. I'm not going to show you how to do it in Lua because there is actually good documentation in it, but this might be part of a future talk. We're going to do it strictly in C. And I have already pre-written some code for this here to show you what a dissector is. So this is packet example C. We do some pre-registration. There is plenty of examples on what to do there. We have some field registrations and stuff like that. But what we have to figure out before we do anything else is, how is this dissector being called? Now, jumping back into Wireshark, when we start our dissection and when we see our packets, we actually see that it's an IPv4 packet, but we need to attach somehow or tell Wireshark somehow that when he sees that packet, he has to call our dissectors. There's multiple ways of doing that. For instance, you can attach to a certain port like HTTP does. So every time Wireshark sees a packet that goes to the IP port 80, then it knows, okay, I have to call the HTTP dissector. In our case, we're going to use this protocol information. So I'm going to say, okay, whenever you see a protocol information 254, then you're going to call my dissector. It says already unknown, so this is good. So I know, okay, there is no other dissector that's using this information, but I need one step further. So I am going to marking that, and then I'm going to look in the bottom line, or I can even create a display filter from that if I want to. And I see, okay, this field is called ip.proto, and I write this name down, because this is what I'm going to have to look up next. So going back to Wireshark, to our source code, what I'm doing is I'm going to search for packet IP, which is the sector for the IP packets. And then I'm going to search for ip.proto. And I'm searching for something that's called register, which I won't find. Well, let's see the next thing. This is gonna just go in for register dissector table. So I see here, okay, I should have looked it up with the question marks, then I would have found it faster. So I see, okay, IP proto, he already knows that. So he knows, okay, there can be some dissectors written for that because there is a dissector table registered for it. I see a little bit more. So I see, okay, this is a register table that's called IP protocol. So this is how he names it. And it's expecting me to have an 8-bit unsigned integer. So basically a value between 0 and 254. The rest I don't care about. I see there are other dissector tables I could have used. For instance, I could have written a dissector for IP options, again, using a number between 0 and 254. And there is something that's called register heuristic dissector list, so register Heu dissector list for IP. Well, in my case, I do know I want to write a dissector for the protocol 254. But there are some instances where you might not know that. So you might know, okay, there is, let's say some protocol out there, and you know, as part of this protocol, your protocol will be transported, but you don't know how, on when, and the entry is not really clear. But you know, if you get all the payload data from that protocol, you can figure out if your protocol is part of that. And this is called heuristic dissection. So basically what happens is you will tell the IP dissector, I'm interested in all your packets. And every packet he gets, he will then send to you. And you will then decide, okay, I'm going to dissect it, or I'm not going to dissect it. This is where the speed live versus offline comes into play. Because this will take you time. You will have to look at each individual byte. You will have to calculate some stuff. For instance, for some protocols, you might calculate some checksum to see if this is a valid combination of bytes. So this will take some time, but there might be other protocols already in line waiting for their heuristic dissection turn. So you have to be really fast in determining, is this for me or isn't it? In our case, we have it easy. We know, okay, we're going to register just for the IP protocol. So I wrote here, we go to the last function here, which is our proto-reg handoff example. This is something that's always in every dissector you see. So this code here, proto-reg handoff, is a fixed string. It always has to be named like that. An example is a value of my choosing. So in this case, because the protocol is named as example, I use it the same way. And here, register now my dissector. I say, okay, this IP proto 254 is what I want to do. The example handle then explains to him, this is an internal value. The second thing I have to do is I have to register my protocol. So again, Proto-Register is a predefined text, which I have to use. An example is again something I chose for myself. Inside there, I will register some fields. I will blah, blah, blah. This is not really important what I do here. I will even register some information and stuff like that. All of those informations, you will have all the documentation in our developer guides. The most important thing that I have to do right up front, though, is this one, Proto-Register Protocol. So what I have to do is I have to register my name for the protocol, a certain value string which should speak out and explain what this protocol is. This is not a description. This is just a long name for the protocol. This is the short name for the protocol. And this is what display filters will look like. So if I want to use a display filter with an uppercase, I start with an uppercase here, but this is a bad example because pretty much every display filter starts with a lowercase. I register my protocol. I can register some preferences here as well. And the last thing I'm gonna do is I say, okay, this is the example protocol. Now I can save this. Let's go to File and Save. But it won't be compiled yet, you know? He's just telling me the U that it's untracked, it's not part of the source code. But if I build now Wireshark, and you can see it in the bottom here, he will build just a few files and none of those are called packet example. The reason for that is I have to also add it to the source code. Now I have two ways of that. CMakeList.txt is the main version where I do that. But I might be building the dissector, for instance, just for my own company and distributing my own version of Wireshark. Then I don't have to put it into CMakeList.txt. I can use a CMakeList custom TXT. The reason behind that is that I won't have to change anything from the Wireshark source code, and the compile files might even reside outside the source code directory, which makes it easier to update my source code stuff or the Wireshark to a newer version. Now, if you go into here, you see pretty much up front, you see a lot of those arrays. You're looking for the first save array, which is now its public headers. We don't need the public headers. We go down there, down there, down there, down there. So, and we here at dissector source. Those are all the dissectors he adds to this program. And the simplest thing here to do would be to search for the first packet that starts with E, because you should always order it. Sorry, he used it with 3. You should always order it alphabetically. It just makes it easier to find. So we're gonna put it in here after the one called Exa place, and we put in here our packet X save, and we hit compile again. Now he will first run CMake again because we changed something. And then he will build a few stuff more because he will say, oh, I have to do something else as well. Well, we do this in a second. So he will build the EPUN again, and then he will say, okay, I'm gonna rebuild all the stuff below. He's jumping to a few errors because, well, let's build the finished one first. I have predefined all those source codes, so I don't have to write it here. And this one will work. Yeah. So let's wait for that. Wireshark still running? Yeah, of course it's still running. Then we have to stop it first, and then we can run it again. So and we can stop right away. Now, ignoring the yellow part now down below, now we have our protocol. So the text example we have chosen before is now part of the list. It doesn't say unknown anymore. And if you open up this one, it still says here unknown, because for IP it's unknown, but we already know, okay, this is called example dissector implementation. As you see, the long text which chosen is part here. And as you can also see, all our information is now also part of the packet view. So we have this remote interface name length, we have a remote interface information, we have a message length and stuff like that, and even have a subpart that's called message data. Now, the neat thing about it is those are all fields that have been created by me, and I can even use that as already as a display filter. So you see, okay, also at the bottom, you see this is called example message length. Now, what did I do there? Let's jump back to the source code and jump back to our first version, which didn't compile at the beginning, but it will compile at the end. So what I did is I said, okay, I want to register my protocol. This protocol then needs to have some kind of function that will basically get the information that I want to have. And this is my dissect example routine. So I have a method, and I go up here. I have a method called dissect example, which will then get all those fields and will start my dissection. Now, in my case, I have a lot of compile errors because I have forgotten to disable the warnings stuff. But you can see that it's getting a DB buffer. This is what I mentioned before. So those are the bytes that have been seen by Wireshark on the network or handed over to Wireshark from the network. You get an internal packet infrastructure, which is basically a lot of stuff like all the packets on top of that. So you can navigate the structure to, for instance, the IP404 and read fields from there if you want to. You get a proto tree information, which is your position inside the protocol element, and some arbitrary data, which doesn't really make sense. What you're doing now is, in this case, is the first part. What you're doing now is you start dissecting your protocol. And one of the first things most protocols do is they set the info column. So when you run Wireshark and you see something in the info column, let's hope he doesn't recompile. No, he shouldn't. It doesn't want to be that fast tonight. So when you start again and see something in the info column, you should always normally have something written here. In my case, this is because this is the other information, we already cleared that. But the thing is, for instance, if you're just using TCP, you're just using IP, then you want to have something written in that area. So let's open, for instance, close some device boot up code. So usually this is what you write in the info column. Keep in mind though that what you ever write in the info column is the last protocol dissected. So you can't go back to an earlier version. So if you need the information, for instance, for user data for the UDP stuff here, you can't easily. What you could do is you could disable this protocol, which I don't think we have a short version for it. You have to go through some online capture stuff, but you could disable the NTP dissection just entirely, and then you see the UDP stuff. So only the last protocol dissected wins in this column. But how you do it? Oh yeah, sure, it clears because I write this one here. So what he does is, the first thing he does actually is he writes the example in it, and then he clears the info column. Those two commands should be vice versa, then it would be correct. Now put the second stuff in and see if this one compiles. So this is a smaller version for the first one, which again has this one, but it has better header fields. So the second thing you do when you dissect, you want to have your information shown someplace. What you have to do is for each information value, you're gonna say, so message we saw, message name length, stuff like that. For each information value, you have to create an HF entity, which holds all the stuff you need to display the information. So in my case, for instance, I have a field here called verification, example verify, and this is one of the neat things you can do. It's a true-false string, so basically it tells me it can either have the value verified or not verified. I can have additional fields. I can, for instance, have here the remote interface name length, the remote interface and stuff like that. This is all part of how the message in the example protocol is being transported. And you already see we don't have a specific hierarchy. So if you have a hierarchy inside your display filters, you have to put it in here. So if you put example.remote.name, you're creating a hierarchy. But this has no other ramifications than the user being able to sort it better. What I then have to do is I have to register my tree because every tree element has to be someplace. And in my case, I also have to register some error information. I come to that in a second. Here I register my HF fields with the protocol. I register my trees with the protocol, and that's that. Expert example and preferences I show you in a second. Now, coming back to Wireshark and our example protocol. It's just neat. I can always start just the dissection and get it. Now, my protocol also has other stuff, for instance. But this is actually, oh, sorry. This is the wrong version. I wanted this one. I have to recompile with this one. So in this example, which is basically the big version of my protocol, I already started my dissection engine. This actually annoys me. This we're going to change in the next item. So the first thing I do is I create my main tree. So this is where everything else will reside under. So in my case, this is then called example dissection protocol, whatever I named it. Is it still running? Oh, I forget to close it every time. So again, this is this tree element here. Going back, what I then do is say, okay, this tree element has some children. And then I just add those. So in my case, I add the remote length. If I go back here, this is also the first element that you're going to see here. I can actually change how this example interface communicates. So I can say, okay, this is message blah blah, and say transmit. And also I can say that the second interface. And you see the information changes, and also here the information changes. The remote length doesn't change because for whatever reason he doesn't see it correctly at the moment, but yeah, we just ignore that. I can then add, in this case, the remote name. So I might have some issue here, which we're gonna fix later. I can add the length and stuff like that. The neat thing is, and this is here now for verify, I can also add additional subtrees. So in my case, I created a second subtree. And I said, okay, I want to see, for instance, have a flag on that, or have some calculation done on that, or whatever. In my case, I say, okay, I have a calculation for payload length, and is this true or not? This verified here in my case is just the last flag of this information. So if I go here, and it should be with the next field, it should be false at some point. This takes a little bit of time to update. Usually it should be false. Well, I might have found a bug. Let's see. Yeah, we might have found a bug. Yeah. We can always do it the other way around. We just create the message, longer message, and say verify. And let's just start with another one. And in this case, it verifies false, but it's still reading the wrong flag. Well, We're not going into detail with that. But how do you add those fields? Coming back to adding those fields. So I added my tree, I added my subtree, stuff like that. I'm still operating on this message buffer. And now you have to calculate and come up with the position of the protocol information. So for instance, the first thing I'm gonna add is my remote length. And bear with me because I usually jump through source code quite big. I'm jumping down now to where I have defined my HF example remote length. And this is here. So I've said, okay, I have this field remote interface name length, which is example remote length as a display filter. And it has this database type uint16, which means it's a 2-byte value, right? So what I'm doing is I'm adding this to my tree. I say, okay, I have this subtree, example tree. I'm adding this HF example remote length stuff. From the message buffer, I'm starting at an offset. The offset initially is 0. I'm adding 2 bytes, which are the next 2 bytes. And I have, is it really 2 bytes? Let's see. Yeah. And I am adding the length. And the length I have read out before. So I'm adding an arbitrary value. I could add here now 16 or 25. I could calculate something, and I'm just adding this value. The important thing is this combination here, offset and 2. So Wireshark, although it knows how long the field is, and it usually just adds those fields if you add to each other. But if you need the offset, you have to keep the offset, track of the offset yourself. So in my case, I just said, okay, this is this field, offset is plus equals 2. And this is just being added to the next step and the next step and the next step. And I'm always adding the information, how far I have to put the offset off in the next step. You see that I can also read the information from the packets and do stuff with it. So for instance, here I read 2 bytes ASCII code. And then return a decimal value. So this read 16-byte ASCII is actually a functionality that's built into Wireshark. So I can look it up. No, in my case, it's my functionality, read 8-byte ASCII, and here's the function that's been built up. So we have a lot of functions that's called TVB, which are, sorry, not the definition, the declaration, which you can use. So if you need to, let's say you need to load some values and calculate on them, then you can go and say, okay, give me the next 8 bytes. You have to have the byte order in mind. This is why there are different versions of each function, but you can read out everything you need to read out. You have different values for different types. For instance, if you read a uint16, it already considers byte order because it always goes from big Indian to little Indian and vice versa, but you can change that with the encoding if you want to. Yeah, and there are a lot of functions. You can read strings, you can read times. There are functions for reading MAC addresses, reading IP addresses. So you don't have to write that functionality. I would recommend whenever you need to read a value that's beyond just 1, 2, 4 byte data value or character value, take a look in dvbuff.h and see if there is a function for that. Because I would guess that in 99% of the cases there is. So I have calculated here my value. I have, in this case, for instance, I'm getting a TVB get string, and reading that offset length, and I'm telling it it's big Indian encoded inside the packet, and then he reads it back to me big Indian encoded. One thing that keeps in mind here is you will go through all this stuff. You will go through other dissectors, and you won't find anything about malloc, alloc, realloc. The reason for that is that to ensure that Wireshark is a very stable program, we have our own memory functions that we use to keep track of the scope of the information. So whenever you see something like this here, WMEM, then that means that we're allocating memory within Wireshark ourselves. And you have to use the same stuff. So there are 3 different scopes that are already predefined, which is WMEM file scope, packet scope, and EPEN scope. And EPAN you can ignore, because this means whenever you read a memory, we have this memory block throughout the lifetime of the program, which is a bad thing because in 99% of the times you won't need it. Packet scope means this memory only exists as long as the packet is being processed. So it's being read throughout the dissection and then thrown away, which is what you want because the information then already is part of the tree. And file scope means as long as the file is open. And file open also means as long as the capture is live. So if you're doing a live capture, you have a file scope. If you stop the capture and restart it, you have another file scope. One thing I'm doing here is I have this captured length remaining. Remember in the beginning when I said that the TV buff you're gonna get is not the TV buff that's on the network, but rather that message or the number of bytes that the caption engine has given to you. So from time to time, when you read ahead and you read more values than you want, then you have to calculate how many bytes do I still have. And for this functionality, we have a lot of remaining stuff. Again, you will find it in tvbuff.h. So in my case, I get the number of bytes still in the TV buffer that have been captured. I do an additional thing. And what I then can do is I can add expert information. And this is one of the last things I want to give to you. Expert information is actually your way of communicating with whoever is using your program or the dissection engine to give him hints or tips or tricks on how to do this stuff properly. So in my case, I have here an error message that says, okay, the calculation for the payload length yielded the result longer than remaining length. So basically, the packet says it has 25 bytes in it, but I only have 5 bytes more from the capture. And this is good sense to have throughout your dissection to constantly check where you need to have additional bytes available for the stuff you're gonna do next. In some scenarios, you don't need to do that. So when you only are within the 64 byte limit of the Ethernet header, you can pretty much assume that you will always have the 64 bytes because this is the smallest amount of bytes you can only capture on an Ethernet interface, except if you're not on an Ethernet interface. But for anything beyond that, I would assume that you would have to calculate from time to time your length. You also have these protocol errors have to be registered. So you have, in this case, example error protocol, example warning protocol. Those are protocol errors. They are marked as such, and you can then say, okay, this is an error or this is a warning. And as you have already seen, those are then displayed in such a way. So you have this expert info, and this expert info is even displayed. It's also inside, so you can look up the expert infos and you can filter for them as well if you want to. W_W as expert, for instance, will give you all packets which contain expert information. It's a good thing. It's a very good thing to do that. There are a bunch of different protocol and warning labels you can give. I would stick to protocol because most of the time you're actually having an issue with the protocol itself, like too few bytes remaining or some irregularities or something doesn't add up because the program has the wrong information inside the protocol and stuff like that. So I would stick with that value. The last thing you can also do with a protocol, and you have seen us do that at bunch, is protocol ref register, full reference, and prefs register, which basically adds some values. So what you do is you create a global value, and then you can create a description and a text for that and have a preference in your program. So for instance, if I go here on the protocol preferences, I see that I have those two values. So show message transmitted as data I can add here. And also I can go get message after n type, and I can say, okay, get message after 10 type, cut message after 10 type, and I can cut my information. This doesn't necessarily have to do anything. You will have obviously write your dissector in such a way that it reacts on that, but you won't have to discuss anything, how to use preferences in Wireshark and stuff like that. So as soon as I open the preferences and I go search for my protocol, I will already find it here. It will have the same information. It will be part of profiles. It will be part of exports. And everybody who uses your protocol will be able to use that. There is one thing I want to mention before I go. You have seen me now write a dissector within Wireshark and within the Wireshark source code to be full disclosure. Obviously, there is also the possibility to write plugins. Wireshark is already providing a few plugins from the start. So when you go to the plugins directory, you see that we do have some plugins. We have codec plugins, we have EPAM plugins, which are dissector plugins, and then we have wiretap plugins, which allows you to, in this case, it's USB dump, to have a different capture interface engine. There is also a demo in here, which is the plugin interface demo. You can do quite a few tricks with plugins. For instance, you can extend the UI, you can add new dialog windows to the UI, and do dissection stuff on your own, which is very powerful. We would avoid putting new dissector code into plugins. There's two reasons for that. First of all, plugins get run last. So you're always at the end of a dissection engine. If another protocol wants to make use of your dissection, then it would require, in most cases, to be a plugin itself. There is ways around that, but it's harder to write for most people. The second thing is plugins. We update more closely stuff that's in EPAN than we do in plugins. They are on top. They are always compiling. We take care of that. But it's just we try to shy away of having plugin stuff. Also, and this is most importantly, most of those plugins are exchanged. So, for instance, if you're working with Siemens and you can get an updated version of the Profinet plugin and install it on your system. And when you have an error with that, we always have to make sure that the error you're transporting to us is actually part of the main source code and not of some third-party version of that plugin. So I would ask you to avoid using plugins if at all possible. But they're there, they can be used, and yeah, they are quite often used, especially for protocols which are exchanged on a daily basis.
Roland, just letting you know there's 8 minutes left.
Thank you. This is actually my end point anyway. So thanks everyone for watching. Let's see, we covered that, and thanks everyone for watching. I hope I gave you a good overview on how to write the sectors, how to write, what to do, what to avoid, what you can do. And I just leave you with, let's code. Let's have some fun writing the sector stuff. They're really easy to do. It's fun to get into Wireshark. It's easy to get into Wireshark with that stuff. And I hope to see you all contributing some code in the future, if you haven't already. If you have any questions, put it in the chat, and I will be in the Discord later on as well. Thank you.